whatever. Good enough place. So, another hour, another room, right? It's the unfortunate student worker luncheon day displacing us, but hopefully this time we'll be okay because we're not in the room where they hold the club meeting for, I guess, what is it?
It's a graduate level class.
Oh yeah, well that one's a graduate level class, the one we just got in the way of. And then the other thing we got into was the club meeting for, like, I want to say home ec or something, I don't know. A bunch of girls. All right, so I was going to attempt to at least sketch the proof of the Generalized Stokes Theorem here. Hopefully I can get through it quickly enough. So his proof, the reason I went through the homology and all that is that he uses it to build up integration on chains. Let's see here. So I guess I need to do some of this to make sense of it. So this is section 6.3 in I always misspell his name. Rentlen. And so he's like, if you have a smooth map from a manifold n to a manifold n, then you can induce a map on the k-chains on M to the k-chains on N. And let's see here. He draws the following picture. He's like, here's Rn. So you've got some kind of chart U. You've got your simplex sigma bar. And then up here you've got some kind of curved space M. You got a patch phi, which takes you up to some sort of curved simplex, right? And then you've got some other curved space over here, N. Your mapping F goes like that. And that gives you some kind of curved simplex F star sigma bar. And to get directly from here to here, it's just F composed with sigma. He says this is the induced map F star on simplices. I guess the question is, so he's talking about the smooth. Well, I guess I should read some of the. Let me read some of the start to this chapter. I don't want to write anything down. I just want to read some. All right. He says simplices and singular simplices tend to have sharp corners where derivatives do not exist. So when dealing with a smooth manifold, we would like to have everything behave nicely with respect to smooth maps. Ideally, we want the map patch sigma, rather phi, that goes from the n simplex to M to be smooth. But smooth maps are only defined in open sets, and our simplices are closed. The way around this is to extend sigma to a smooth map. More precisely, a smooth singular M simplex sigma is an equivalence class of triples, where sigma bar is a M simplex and U is an open neighborhood of the affine sigma bar, which is the smallest affine subspace containing sigma bar, blah, 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 blah. Basically, the point is you have to take the simplex and extend to an open set in a smooth way, and then that is what you put onto the manifold to get a triangulation. And this leads to the so-called smooth singular homology. And we have a theorem which is simply this, that the smooth singular homology of M is the same as the homology of M, which we've been calculating the homology before, but if we use the smooth triangulation, then it's the same. Now, in any event, the good thing is, what I'm failing to see at the moment is the connection between chains and form integration. I don't quite get it yet. Oh. Okay. Oh, well, that's dumb. Well, that's dumb. How would you... That's so dumb. How would you integrate? How would you integrate? How would you integrate, like, if you had a, you know, the sum over, like, let's say, oh, good grief, I don't even know the right notation for it. Let me just write what he writes and try to explain it. Omega is integrated over sigma is by definition the integral over sigma bar k of phi star omega. And so what's going on here is just this. You can define the integral over a smooth M chain. You just define to be the integral basically of the pullback of the simplices back here, like that. And then of course we know how to integrate. We know how to integrate over, you know, solid polytopes in Rn. Like that, we have a multivariate theory of integration there. And so it's the same thing as the pullback of the form integration, where we just pull back the formula from the form back to the, it's essentially the same definition. But we can replicate that idea for M chains, because we can pull back to the integral over polytopes, basically. And that's all spelled out in more detail in the book here, and my apologies for not being more explicit about all that. Let's see here. And he has some like change of variables theorems. And, yeah, anyway, let me get to the proof here. Hopefully we can appreciate the proof. As follows. Let's try it out. So this is Stokes' theorem. Theorem 6.4, page 164 in Rantlin. And again, I'm just being very sketchy. So it says that for any K form, omega and K plus 1 chain C. Oh, okay, so I'm sorry, I'm burying the lead here. The reason the triangulation is nice is because it's giving us a systematic way of describing a subset of a manifold which pulls naturally back to a sort of canonical subset of Rn, where we can do integration. You know, so the roadmap for how we pull back the differential form, we already know that. But now we also have a roadmap for how to take a token like subset of M and bring it back to here. But if we can do it for the token subset, and then that token subset can be used to like build M through a triangulation, then we can extend the theorem to like everything. This would be analogous to what I do in Calculus 3, where I prove the theorems for like a standard shape and then point out that, well, you can replicate that shape over and over and over again and as such fill out the whole space. Anyway, I give arguments like this. This is somewhat akin to that. Anyway, let me get to it. Being slightly fuzzy here. But anyway, here it is. So we've got a chain, C, a k plus 1 chain, integrate d omega. That's allegedly the integral over the boundary of the chain, omega. All right? And then he says, in the next section, we'll show how Stokes' theorem works for infinite chains, that's non-compact manifolds with boundary, provided we restrict ourselves to differential forms with compact support, blah, 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 blah. And maybe we'll get into that stuff next semester if we play our cards right. We'll see, all right? But let's do this here. So he says, by linearity, it suffices to show that the integral on a simplex, integral sigma d omega is equal to the integral over the boundary of the simplex omega, I believe. Yeah, for some k plus 1 simplex sigma. Because if we can show that, then what's the chain? Remember that the chain is like a sum over like, you know, a sub I, sigma sub I, right? And then basically by the linearity of the boundary operator and the way this all works, if you can prove it for the simplex, then you can extend to the chain. And if you can do a chain, well then that's a lot of things. So, okay, anyway, how do we do that? So, he says this is equivalent to, he says if sigma is equal to S bar k plus 1 u phi, then we face, he's saying this is the calculation that we have to integrate. We have to show that the integral over S bar k plus 1 of the exterior derivative of the pullback under phi of omega is equal to the integral over S bar k plus 1 of sigma star pullback of, so here we're just using the property of the pullback that it commutes with the exterior derivative, and so that would be integral over sigma of d omega. Some of these steps are identities, other of these steps are like what we want to show, I think. I'm just going to keep writing down and we'll comment once I'm done writing here. All right, let me think about this. So I think the way to read this calculation, right? I think the way to read this calculation is inside out. So this is equal to that, and that is equal to that. Like, we want to prove this is equal to this. But what this means is that you pull back the simplex on the manifold. This is his notation for the standard simplex. This is actually like like a unit triangle, a unit k plus 1 triangle, I think. Something like that. It's like the standard unit polytope. I'm pretty sure that's his notation. We'll find out soon when we get into the details. If I'm wrong, it'll become in my face glaringly obvious. But I'm pretty sure that this is the standard polytope, the standard, all right, standard simplex. And this, of course, that's just the property of the pullback, that the pullback differentiates, commutes with the exterior derivative. We proved that the other day, right? It's still true in this context. And yeah. And this is just what we mean by this integral. So the integral over the boundary of the simplex is by definition the integral over the boundary of the pullback of the simplex to the boundary of the simplex, which is pullback. Yeah. So long story short, it suffices then, it's enough to show that the integral over s bar k plus 1 of, let's see here, which one do I want to do? Which one is the easier one to pick at? Oh, I see. Well, d lambda is equal to the integral over lambda of the boundary of s bar k plus 1. So basically, instead of sentencing yourself to prove a bunch of things about this, right? Just give that thing a name, call it lambda, right? So if we can prove this, then we got it. All right. And that's for lambda, a k-form on a neighborhood U of the standard k plus 1 simplex. So this sk plus 1 is a subset of r k plus 1, okay? It's the standard. And of course, this notation is at odds with my usual sphere notation or circle notation, right? But if you don't tell anybody, I won't tell anybody.
So that's the standard W. K plus 1.
Yeah, I think so. Like, goodness. Well, anyway, we'll find out soon, right? We'll find out soon. I mean, this is what happens when you skip 10 pages of a book and try to jump into a proof, right? And these are the consequences, and we're going to deal with them one misunderstanding at a time. I think I can erase this stuff here. And again, if it's not clear enough already, like I recommend this book for like, if you want just a nice, quick, sort of leisurely understanding of how manifolds work and how they interface with, mathematical physics. It's really hard to beat Rentlen. Rentlen's a wonderful book. I don't think it's the right book to learn careful manifold theory out of, but it's a wonderful book for intuition. The right book to learn careful manifold theory out of, in my view, is probably John Lee's book. And if you want careful mathematical physics of the style of Rentlen, probably Jeffrey Lee's book is the other thing to look at.
Should I get this book?
Rentlen? I don't think you need to buy it. I have several copies. Once I finish my home renovation, I'll have a, hopefully soon. You can borrow mine after today. I'm not using it, so you can take it and read it as much as you need to. Because past right now, I don't think I'll need it. I just needed it for this. All right. Let's get to it before the students come. So, again, by linearity, it's enough to prove. Did I move my camera? I think I moved the camera, but I've forgotten if I actually did. All right. All right, so it's enough to look at lambda equal to a function, a. It's a function of x1, x2, all the way out through xk plus 1. And then you got yourself dx1, wedge dx2, wedge dxk. All right. And then what's d lambda? By definition, it is minus 1 to the k, partial a partial x k plus 1. And then you got yourself dx1 wedge, dx2 wedge, dxk wedge, dxk plus 1. Now that's a little bit sneaky. Let me try to explain what's going on in here. He says by linearity, it's enough to prove it for a monomial of this particular form. So like an arbitrary k form on Rk plus 1, well, what's that look like? I mean, if you think about it, an arbitrary k form on Rk plus 1, right? So you understand here, lambda is a k form in, this is a k form in, this is a k form in R over Rk plus 1, right? Well, it's pretty much manifest in the fact that you've got coordinates that go all the way out to xk plus 1, right? But the thing is, an arbitrary k form would be what? It would be like a linear combination of things like this, right? In fact, there'd be k possible, I believe k possible maybe k plus 1. I think k plus 1 possible forms of this type. Like, because if you think about how many k forms are there in Rk plus 1? Well, there's k plus 1 choose k, which I believe is k plus 1 possibilities. So there's k plus 1 possible monomials like this that you're taking the sum of. But the thing is, because of the linearity of the problem we're looking at, if we can prove it for this, then by the basically by the combinatorial similarity of all the different terms, it suffices to prove it for this. And we can try to convince ourselves of that if we need to. But let's focus on what he says is sufficient to prove, having understood that this is not the general proof, of course. So we got to do that. We got to calculate that integral. How do we do it? I guess we need to come to terms with, do you understand why that's the exterior derivative of this? Because when you're working in Rk plus 1 and you start with this wedge product, the only thing you can do non-trivially is this one. So the exterior derivative of the coefficient function, yeah, it's got a dx1 term, a dx2 term, dxk term, but those all wedge to 0 because there's already a dx1 through dxk here. So when you take the wedge product of the exterior derivative of the coefficient, it just remains the k plus 1. And the cost of taking the dxk plus 1 all the way to the end is this minus 1 to the k factor. That's why that's there. Now, all right, so here we go. The integral over the k plus 1th standard simplex of d lambda is equal to minus 1 to the k. And then we've got the integral over the k plus 1 standard simplex, partial a, partial x, k plus 1, dx 1 wedge, wedge dx k plus 1. All right. And here's what that means in detail. So I think this is, you're going to be able to see the standard simplex in action here. Minus 1 to the k, the integral over, get this, x sub I, x, the ith coordinate greater than or equal to 0. All right. And the sum, I equals 1 to k, of the ith coordinates summing less than or equal to 1. That gets a dx1, dx2, all the way out to dxk. And then the inside integral is 0 to 1 minus the sum I equals 1 to k of x upper I, partial a, partial x k plus 1, dxk plus 1. So we dropped the wedges and we performed the iterated integral over the space. Let me foolishly attempt this for k equals to 2. So that would be R3, right? We'd be looking inside R3, right? RS3. So we're saying integral 0 to 1 minus x minus y integral partial a partial z dz. And what's going on here? You've got x and y greater than or equal to 0, and x plus y less than or equal to 1. So I believe what we're looking at here is the thing I always make Calc 3 students integrate over and watch them fail. I wish that wasn't the case, but come on, people. This is the thing. Well, I mean, it's fine. It's ugly. Fair enough. It's ugly, but this one. So what you got here is x plus y plus z equal to 1, I think. I could be wrong about this.
That's right.
Oh, this isn't quite right, though, because that's not quite it. Because the sum is less than or equal to 1. Oh, yeah, that's what it, well, yeah, okay. Yeah. Sorry, I'm trying to see convex combinations, but I don't guess it's that. But I think this is what's going on. I mean, if I'm right, then the definition that was given earlier for S bar k plus 1 is the convex hull of E1, E2, EK plus 1, where that's the standard basis. So like the convex hull of E1, E2, E3, and R3 is this standard tetrahedron bounded by the coordinate planes. Anyway. Yeah, we're having a class in here at the moment. Sorry. That won't be the last time that happens. What time are we at? 11 what?
37.
Right. I got to wrap this up in about 10 minutes. So anyway, then you do the usual integration, and you get, minus 1 to the k, the integral of, let me call this stuff here Pac-Man. Same song and dance, right? dx1 dxk, and then this last business gives you what? Well, it gives you a of x1 through xk, comma, 1 minus the sum k I equals 1 to k of x sub I, x sub I rather, and then minus x1 through xk with a 0 here. All right. But then the rest of the proof is just that if you look at the, I think we're going to have to stop in here. Otherwise, we're going to have just an unending string of students walking in. This may be enough for you to see it. I don't know. The integral, when we do the integral over the boundary of sk plus 1, what's it look like? So like when you look at the integral over the boundary of s bar k plus 1 of lambda, right? You've got like the integral, right? And you got your a, right? And basically what's going on is you've got x1, and then you've got, you know, let's say the jth one is equal to 0, and then x, you know, k plus 1, right? And then you've got your like dx1 wedge wedge dxj hat wedge wedge dx k plus 1. And when you do that and you sort through the details, you're exactly, and there's two of them, if I remember right. No. Well, yeah, there's the so like there's going to be the one piece of the boundary that's from like this piece, this part of it, right? Well, how to say this? If I look at, well, I don't know. I'd have to get through the details, but basically we just sort through what is the boundary of the k plus 1 simplex. I mean, he works through it and he shows that we get exactly these same terms here, and you generate like the appropriate minuses because of the wedges and everything. Anyway, I hope that's enough for you to see how it's going to go. Unfortunately, my time is up. I locked the other door, but anyway, again, you can read the other details if you're interested. It's section 6.3 in Rentland, and it's really, the rest of it's just straightforward multivariate calculus, but it does probably take another half hour of careful reasoning through the boundary stuff to really see it. So, I don't know. Maybe one of these days I'll actually do it, but anyway, sorry, that's where we got to this semester, so. In any event, next time we'll do the E&M, electromagnetism in differential forms, and hopefully Poincaré's lemma. And that should be pretty much it for this semester.